video, we want to see whether the sum from n equals 1 to infinity of negative 1 to the n times the integral from n to n plus 1 of e to negative x over x dx converges or diverges. So let's define our sequence b sub n to be the integral from n to n plus 1 of e to negative x over x dx. And for here, we want to use the alternating series test. So we want to show that it's decreasing, it's positive, and the limit goes to 0. So the easiest one is to say, well, let's start with the decreasing one. So we'll define e to negative x over x to be f of x, and the derivative is negative e to negative x over x plus 1 times x plus 1 over x squared. Clearly, this thing is going to be negative when x is a positive value. So that means that f is decreasing. So e to negative x over x is decreasing. So that means that we're taking the integral of a decreasing function. So if we take the integral from n plus 1 to n plus 2, that's going to be less than the integral from n to n plus 1. Because at n plus 2, it's smaller than at n plus 1. And at n plus 1, it's smaller than at n. So b sub n then is decreasing. Now let's take a look at the limit. So we need to take the limit as n approaches infinity of this. So we know that, just ignoring the limit part, we know that at n, e to negative x over x is greater than e to negative x over x. Right? Because x here ranges between n and n plus 1. So it's going to reach its maximum value when x equals n. So that's why we have less than or equal to. And so this integral is bounded by 0 because we said this is positive, so it's always going to be positive. So you're integrating positive values. And it's going to be between e to negative n over n based off this inequality here. So technically I should have put less than or equal to here. And now we can just evaluate this. Notice that this integral does not depend on x. There's no x in here. So it just, when I integrate, it's going to be e to the negative n over n times x. And then x will plug in n plus 1 and then plug in n. So that's what we have here. We factor out the e to the negative n over n, plug in n plus 1, minus plug in n. And this just simplifies to e to the negative n over n. So we have b sub n in the middle, bounded below by 0 and above by e to the negative n over n. If I take the limit of both 0 and e to the negative n over n, I'm going to get 0. So by the squeeze theorem, the integral has to be 0 as well. So we showed that b sub n is decreasing, the limit is 0, and we talked about why b sub n is positive since we're integrating over positive values and positive numbers. So by the alternating series test, the original sum also converges. Now, we want to see if it converges absolutely. So we're going to take the absolute value of the inside, and the negative 1 to the n is going to cancel. So we're just left with the integral. Now, we can use the additive property of integrals. So basically, when you take the sum from n equals 1 to infinity of the integral of n to n plus 1, that's just the same thing as saying integral from 1 to infinity of e to the negative x over x dx. And if we look at just e to the negative x, the integral of that from 1 to infinity, that's just 1 over e. And if I divide it by x, if I divide this integral by x, it's going to be less than or equal to this integral. Just when you divide by x, you're making this thing smaller. You're making whatever's inside the integral smaller. And so by the direct comparison test, it converges. So basically, we found something bigger that converges. That is the integral from 1 to infinity of e to negative x dx. So anything smaller will also converge. And that's by the direct comparison test. So this converges absolutely.